and to discuss this joint project with Vladimiro Benedetti, Michele Bolognesi, and Laurent Manivel. So I have started with some couple of disclaimers. So first of all, so this talk is going to be about some very specific objects. So I'm afraid you will not see any very general theorem or statement. There will be some very special objects, and we think they might be interesting. So it's mostly related to very specific examples on one side. And on the other side, this is a derived workshop, but I'm afraid there will be no derived category in this talk. So, so yeah, I hope you forgive me for that. Right, so let me start with some character that will be prominent in this talk. So moduli of bundles. On curve. This is a very classical object. Let me remind it to you. So I work over in complex numbers. Probably can work in more general situations, but let it be like that. So I let C be a smooth projective curve genus G. Be smooth, so sometimes I write like CG, I want to remember the genus, and so I fix rank on D, degree, and write. So U over C RD, this is the moduli space of semistable vector bundles. On C with rank R and degree D. Right, and we have this version URD or SURD. So for a given line bundle of degree D over C, we write SU CRD, oh sorry, RL for the the moduli space of semistable vector bundles on C of rank R and determinant L, which is to say the fiber of the determinant map over the point corresponding to L. Of the determinant map going from mu CRD to P. Right, and we know that this variety as UCRL is a projective variety, irreducible of dimension R square minus 1 G minus 1. And this variety has several nice properties. It has Lorentzian singularity, and it is a Fano variety. It has Lorentzian singularity, so the dualizing sheaf, so the canonical bundle, in this case the dual. Its dual, the anti-canonical line bundle is ample, so it is Fano, and it is Fano of index 2. well, yeah. And it is smooth away from the singular locus of this variety consists of the strictly semistable locus. Well, except for Rg equal to 2, 2. And so on. So I just want to say that we know anything about this variety. But what we would like to analyze today is, can we give a explicit description in terms of equations into some bigger varieties? Can we describe this variety as explicitly as possible? So, I mean, we have a bunch of features of these varieties which are well known, but the question is, so try to describe the goals. One of the goals today is to try to describe this SU-CRD as explicitly as possible, at least for small R and G. So this is one of the goals today, and yeah, maybe I should say something about this. Yeah. I mean, I want to describe this in terms of equations into some bigger space. So one of the things that might be of interest here is to describe some maps to projective space. And this is related to the statement that I put there. This is final of index 2, so there should be some ample generator of the Picard group, some line bundle. Maybe let me introduce this line bundle because it will be interesting later. So one ingredient is the so-called theta map. So I consider, well, I let A be the Jacobian of C, so the Abelian variety Jacobian of C. I let theta be the theta divisor. Of J, of A. So theta would be, we can see theta in a most canonical way in, if we see the surface as peak G minus 1. So this will be the line bundles that have a section. Right, and using this divisor, we can define this theta map. So theta R, we go from SU, okay. So when I forget the line bundle, it means that the line bundle is trivial, just 0. It will be a rational map to R theta. So R times this divisor here. And will be defined in a kind of set theoretic way by sending E to the line bundles in G minus 1, such that, well, not that they have a section, but they have a section with that tensor with E. And well, this is a set. We can be given a scheme structure, so again, it is a well-defined divisor, and it turns out that it's a divisor of class r theta, r times this. You may convince yourself of this by choosing E to be r times the trivial. In that case, it will be clear. And so this is a rational map. And so if I take this projective space here, and I take O1, and I pull back O1, with O1 is the generator of the theta-group. So, yeah. So I want to describe this SU, maybe using this kind of ingredients and this kind of projective geometry in a certain way. Right. Questions so far? Right. So the ingredient, the main ingredient that I would like to use to describe these moduli spaces is this Coble hypersurfaces. Let me explain that to you. So Coble, around 1860 or so, defined.
Why does it, maybe you said, but why does it land in the linear system of r theta?
I think you mean this R, right?
Yeah.
I think you can convince yourself of this by choosing E to be the trivial, R times the trivial. In that case,
sure.
Just, yeah. Right, so these Coble hypersurfaces were found by Coble, maybe almost 150 years ago, and they are two very special hypersurfaces that have unique features. So they are gamma 3 in P8 and gamma 4 in P7. So this index denotes the degree, so a cubic and a quartic in such a projective space. So they have this unique feature. So the singularity, the singular locus of gamma 3 is just A. So this A for a curve of genus 2 now. Maybe let me write A of C2, just to make it clear that we are working on genus 2. And this is embedded by 3 theta. Maybe 3 theta 2, right? And the singularities, the singular locus of gamma 4 is on the other side, on the other hand, this Kummer threefold of C3. Let me tell you what that is. Well, of course, you know that. So the Kummer threefold is just the image of a C3, I'm sorry, via the linear system 2 theta. So you know that the linear system theta is ample. So I mean, the divisor theta is ample. Some multiple of it would be very ample, but so the second multiple is contracts some stuff. So the image of 2 theta will actually be the Kummer variety. It's just a quotient of the Abelian variety by evolution. And this also happens in genus 2, right? And 3 theta, on the other hand, is very ample. So this guy here, this surface here, is embedded by 3 theta into E8. And this surface here just maps to P7, and its image is this Kummer 3. And these hypersurfaces have this funny property that their singular locus is precisely this. And also they are unique in this sense. So it means that the only cubic singular whose singular locus is precisely this surface is the Coble cubic, and the only quartic singular along this Coble threefold is the Coble cubic. So they are kind of uniquely determined by this geometry here, and
they depend on the curve, right? So for every curve, you have this thing.
Yes. I mean, maybe it is not clear from the relation.
Unique.
Yeah, unique with respect to this property. I mean, I take C2, one curve with genus 2, and I embed its surface by 3 theta. I have a surface, and then what I get this surface is a unique. Is it clear?
And what if C3 is hyperelliptic?
Oh, if it's hyperelliptic, I don't remember very well, but I think the picture is no longer it doesn't work. I think yes, I have to make some. I should be more precise about the nature of the curves. So the curve C3 shouldn't be hyperelliptic.
Are they like images? Are they like chord varieties?
Could you say it again?
Are they like chord varieties of the singular locus or something?
Oh, in some sense, some secants or something like that. Yeah, I will try to describe that in a second. Oh, I should start from the top, right? No problem. Good. So at this point, there's no relation between 1 and 2. Let me come to that in a second. So, yeah, maybe I should also say that these hypersurfaces have more special property. For instance, they have some duality, the property with respect to duality. Gamma 4, for instance, is self-dual, so they have some funny geometric properties and unique ones. Probably will come to that later. Right, so maybe you could ask, so how do you relate 1 and 2? So this started with an observation by Narasimhan and Ramanan. So they proved that SUC32 is actually isomorphic to gamma 4. Okay, so this is the kind of description I want to make. An explicit description of the moduli space, just as a hypersurface. Okay, very special one. And I still didn't tell you how to define it, right? This hypersurface. But this is the kind of statement that I'm aiming to. Okay. So actually, they proved that gamma 4 was the image of theta 2, and then we will show that theta 2 was actually by theta 2. Right. So SU has a map to P7 by theta 2, and the image of this map is gamma 4, and actually this map is an embedding, and so it is really an isomorphic. Okay. Right. So this kind of thing, and right. So, and the next case would be for this Coble cubic. So for gamma 3, so you take again theta 3. This was from SU. So this time I work in genus 2. And I go to 3 theta. And it is, one can prove that theta 3 is a morphism, and actually a finite morphism, and actually a 2-to-1 color. And so there is a branch locus, which we call delta. Theta 3. It was conjectured by Dolgachev and proved by Ortega and Guillen independently that this branch locus, so this is a sextic. That this sextic is actually the dual of gamma 3, the projective dual of gamma 3. So you describe the moduli space as a 2-to-1 cover branched along a sextic, and this sextic you describe the Coble cubic as just its classical projection. Okay. So this is the kind of description, of explicit, in a sense, description that I want to make. And the goal would be, so this goal would be to provide similar descriptions for other moduli spaces.
Is gamma 4 known to be rational?
I beg your pardon?
Is gamma 4 rational? No,
Gamma 4, I think yes. Gamma 4 is rational. Okay. So, where should we find for similar descriptions if we want to give them for other moduli spaces? So the answer is, well, not the answer, but a possible answer is to look into Vinberg representations. So I will be very sloppy here, unfortunately. So, but let me just give you the main ingredients of this. So one should start with oops. One should start with a reductive, the algebra. I think maybe you can even start with a simple one. And equip this with a grading. So this grading could be a Z grading or a cyclic grading. And you know, this grading, the Lie bracket should respect this grading. And for instance, you could take some height grading. So this would come from, you write G as a Cartan subalgebra plus some root spaces, and for alpha in a root, there is a way to write alpha as a sum with integral coefficients of some roots, maybe n, where alpha 1, alpha n is a set of simple roots. So, and well, there are many ways to choose height, but the simplest one is to choose k. So alpha k, choose a root from delta, and let h be our height function. Height function of a root be the coefficient nk. So I just look at the coefficient, the case coefficient of the root in its expression here. So this is going to belong to z. And then, g0 will be h plus the sums of the root spaces that have height 0, and gk, gi be the sum of roots of height I. This kind of things you can do with your algebra with very and there are very easy combinatorial rules to describe this. There's G0 and the eigenspaces Gi. Or another way to obtain gradings is if you have a Lie algebra automorphism, then the eigenspaces for the automorphism will also provide a grade. Yeah, maybe, I don't know, for instance, if you take a G equal to what, E7, and you choose 1, 2, 3, and so on. You choose alpha k equal to alpha 2, so the delta here is just alpha 1 up to alpha 7. They are indexed by the root, by the vertices of the linking diagram. So if you want to understand what G0 is, you just have to color this one. So G0 will actually be GL7, and then G1, I think it should be the adjacent guy here. So this is wedge 3 of C7. And then there is probably G2, which I think is a C7 again. And G, the whole G is G0 plus G minus 1 plus G1 plus G minus 2 plus G2. You can do this kind of tricks to decompose your alpha. So another way to construct gratings.
Daniele, problem 22 is more canonically lambda 6 of C7.
Okay, if you wish. Or maybe C7 dual.
There is a natural operation.
Yeah. Okay, thanks. Another instance of gratings will be, it appears from grading induced by cyclic automorphism. Of G. For instance, I think, for instance, E8 has a 3-cyclic automorphism. And then this gives a decomposition, a grading.
Recycling means order 3.
Yes, order 3. Yeah, maybe write it like that, if you prefer. And this gives a decomposition. So the 0 eigenspace will be GL7. The 1 eigenspace will be wedge 3 of C7. No, SL9, I'm sorry. So this is SL9. Yeah. And then wedge 3 of C9. And then wedge 6 of C9. This would be G0. This would be G1. This would be G2. And this side. Yeah. So this is the kind of thing you can do. And so one nice thing about these gradings is that for Z gradings, so the fact is that so G0 is the Lie algebra of some group V, and G0 acts on G1 with finitely many orbitals. So this is important because so we will see in a second that this datum is somehow related to datum 2, and from this observation, actually we can construct some degeneracy loci related to the orbits of G0 on G1, which give rise to interesting subvarieties of Grassmannians. Okay, let me not go into much more detail about that. There's a lot to say about these representations, but this is just a sketch.
Is the adjoint representation? This is the adjoint representation?
Which one?
G0 on one.
It behaves sort of like the adjoint, but I don't think it is the adjoint representation, strictly speaking. It has many of the features of the adjoint representation. There is a Cartan subspace here, and you can study invariance. So if you look at so C of G1, G0, this is actually C of H, some H, the Cartan space, W, where W is a complex reflection group. which is not real in this case, but still this ring of invariants will be just a polynomial, a free polynomial ring. Okay, so it has many features of the adjoint representation, like this, but it is defined in a different way, and it gives rise to different orbits and so on. Okay, good. So now let's try to. Oh, I'm sorry. Let's try to go from one thing to the other, at least by means of an example. So relate a Vinberg and Coble. These two guys are very interesting, and we try to relate them. So this is actually work by Luzon and Sam. Or also there's another very nice paper by Luzon, maybe last Bayman. There's another paper also by Askevich. So for instance, we take this example here. So I should take an element.
By the way, Daniele, in this example, the number of orbits is infinite.
Yes, so yeah. I didn't want to go very much into that, but yeah. The finding many orbits appear in the Z grading case. For cyclic gradings, we are in the so-called tame situation. So the number of orbits is infinite, but it is somehow under control. This is related to affine thinking diagrams. Yeah. So in this case, the number of orbits is infinite. Yeah. But yeah, precisely we take this case here. Let me write V9 just to fix this back to space. And I take it to be general enough. There's a very precise notion of what should be general here, but let me not go into that for the moment. So how do we get this Coble? So we should get some Coble cubic from this guy. So we do it this way. So we identify wedge 3 of V9 with H0 of omega 2 of 3 over P of V9. So by, it is easy to compute the global sections of this vector bundle, and this set of global sections is naturally identified with wedge 3. Yeah, this is kind of easy. And so now the vector here will give me an element here. So I see this as maps from tangent bundle of P9 of P of V9, maybe with a -1 to omega of P of V9, maybe with a 2, and alternating maps. Because this is wedge 2, so the map from here to here, it is H0, this dual tensor this. But if I take it to be alternating, it will be in the wedge 2, it will be a skew symmetric map. Skew symmetric, and this is a vector bundle of rank 8, equipped with a skew symmetric endomorphism. So you can look at Pfaffians of this endomorphism. So the Pfaffian of degree 8 will be a hypersurface in principle. And we can compute the degree of this hypersurface. So it's a Pfaffian. Pfaffian is the square root of determinant. If we look at the degree of this hypersurface, so the vanishing of the Pfaffian 8 is a hypersurface of degree. So 1/2 of something because it's the square root, and then just say the C1 of omega 2 minus the C1 of tangent of -1, and you compute this as 3. So it's a cubic, and it's singular about along the sub-Pfaffian locus. This is a typical behavior of determinant of Pfaffian varieties. And this happens in codimension 6. And you compute, this guy is an Abelian surface. And yeah, in the end, it turns out that this B of Pfaffian 8 is precisely the Coble cube. Right. So this is what happens in this case. And we would like to generalize, so no, not to generalize, but to give similar interpretations for different moduli spaces.
I'm sorry, and if you consider the next locus, is it the singular locus of the
sorry, this one is the Coble cubic. Coble. Yeah.
Yes.
Yeah, I'm sorry.
In this case, it is an Abelian.
Yeah, this one is A of C2 of some curve. Okay. And the next locus is empty.
And also, this definition, this surface comes with a natural rank 4 vector bundle.
Right. Yes. Yes. So it turns out that the this vector bundle is related to the linear subspaces of maximal dimension contained in this cubic. And yeah, such if you take such space, there's some story that one can tell here to identify the level 3 structure on this Abelian surface using this, but it's a bit involved. Anyway, yeah. So, and by the way, let me mention quickly some kind of motivation. So our original motivation, well, this is maybe in parentheses because this is not really essential, but so let me just say that we were motivated by the research for interesting final varieties that could appear as linear sections of such degeneracy loci. Let me mention this quickly for this example. For instance, here, if I take a codimension 3 linear section of gamma 3 and get a cubic fourfold, which is a linear section of cubic. And there's this observation, this remark, that a y or cubic, a smooth cubic fourfold is in C18, the Hasset divisor of cubic fourfold is H2 discriminant of degree 18. Now, if and only if y arises this way. So the C18 consists of cubics which are linear section of Coble cubic. Well, if you want to 18, yeah, C18 this was considered by Addington, Addington, therefore, Addington, Finkel, Varado. I'm sorry. Yeah. And yeah, maybe idea of why this should be true is that, well, if you start with a linear section of gamma 3, then if I take this map here, this resolution, so this this V, and I restrict it to P5, then I get something like this. So here it will split out 3 copies of the trivial. And here there will be some vector bundle, which I call F1. F is a vector bundle on Y, and so if I take a non-zero global section of F, then it may be generic. Then the vanishing locus is a del pezzo surface of degree 6 contained in Y. So Y is in P18. And conversely, if Y is in C18, then Y contains such a del pezzo surface of degree 6. Then we get a vector bundle F by the surface fraction. So there is a way to obtain vector bundles of rank 2 under certain conditions from subvarieties of codimension 2. It generalizes the correspondence between divisors and line bundles. And so from such surface you obtain F, and then from F you obtain this resolution. You get V by kind of Beilinson resolution. Of F. So you take F, which you have, you extend it to P5, and you look at its Beilinson resolution, you obtain something like this. So this means that this map comes from some V on a bigger space, which is just an alternating report. So this example suggested that we could perhaps obtain some interesting Fano or K3-like varieties by considering such degeneracy loci, and this was part of our motivation. This is why I mention it here. Well, so let me come to our descriptions of moduli spaces.
And does gamma T has a nice resolution of singularities?
Yeah. Yes, it does. So, to obtain a resolution of singularities is quite natural in this framework with degeneracy loci, in the sense that many times you can work in a bigger, slightly bigger space, some flag manifold or something like that. So you have some collapsing or projection from a bigger space where you can see your degeneracy locus in a almost isomorphic way, and frequently in a non-singular version.
Yeah, but I mean here the natural thing will give you a generically P1 bundle, no resolution.
Correct. Yeah. This one, yeah. The P1 bundle I think will be smooth. Yeah, because it will be a sort of a stratification, yeah, kind of a sort of blow up. Will kind of blow up the rank, the locus where the sheaf has a higher rank. Yes. This one is.
But this is a generically P1 bundle. And is there some negative resolution?
Oh yeah, I think so. Yeah. So the point is that if you look at it, if you look at the same datum, this V. So I don't remember the resolution on the top of my head, but if you take the same datum V in a bigger flag manifold, the point is I don't remember precisely which one, but inside that it will be, the degeneracy locus will be smooth, and it will project. Okay, right. So, okay. So I still haven't told you what we do. So Moduli spaces and degeneracy loci. Again for G are equal to 2, 3, or 3, 2. But this time we'll be on the odd moduli spaces, not on the even guys. So here 1 like this. So I start this time with the element in wedge 4 of V8. So this datum, by the way, is the same datum that allows to construct gamma 4. Okay. Right. And then there are degeneracy loci. So D of, okay, let me write it like this: Z1 D inside G2 D8, and also D Z6B. So the index here denotes the codimension inside here, and this one is just a quadric section, and this one is isomorphic with SU of C3 with 2 and with P point in C3. or maybe I should write OP to match the notation from the beginning. Or so the singularities of the first degeneracy locus is precisely the second degeneracy locus. And Q is unique with this property. So this has the same features of the Coble cubic in some sense, or in the sense that it's a hypersurface which depends on some choice here, and it is singular along the moduli space. Well, sort of, right? I mean, it has this sort of the same properties as the Coble cubic. It's singular precisely on the moduli space, and it is the unique quadric section with this property. And theorem 2, do I have the micro theorem 2? 2 minutes. It's the same kind of statement, but for G3. So that V again be an element of wedge 3, V9 generic. Then there are loci which I could describe. Yeah. So D again, Z1 of B, D, Z5 of B, D, Z10 of B. That is inside G3 B9. And with the so the singular locus of this guy should be this one. The singular locus of the second one should be the third one. And Z10 is isomorphic with SU3 of O of P. And here we have a genus 2 curve. And yeah. And maybe just a last word. If I try to connect with about 5. So if I try to connect with this topic of looking for interesting sub varieties of these loci by taking linear sections, what I can say is that G 2, okay, this one, if I cut it, okay, this time it is more natural to take not linear sections, not sections of O1, but sections of a tautological bundle here. So I will cut with smaller Grassmannians with a V6, intersected with this guy, for instance, to OP. It will be a K3 of genus 13. And G3 yes. Yes. So let me say just a word about that. This is C3, this is C2. This is a K3 of genus. What is it? Not 26. 19. Yeah, this was actually described recently by Mukai and Kanemitsu. So I think their construction is more efficient than ours because their construction gives rise to a general K3 of such genus, while our construction doesn't, because so their construction actually amounts to take the same thing but letting this point vary. Okay, so they take two copies of this moduli space, but one for one point and another for another point, right? And this gives a further one-dimensional parameter in their modular description, and this affords a general K3 surface. Our construction is maybe more efficient to compute the invariants and the singularities, which are absent of a K3 surface, and whether this locus is connected and so on. So I think both constructions have their advantages. But anyway, this is definitely the same kind of story here. And yeah, we get the same. And I wanted to describe these loci, but I'm way out of time, so let me just stop.